My name is Meghal, and today I'm going to tell you about interactive error correcting codes. This work was conducted by me, Professor Yael Kalai at MIT, and MIT graduate student Rachel Zhang. So let me begin with the setting that motivates the question we're trying to answer here. So we have a party, Alice, the sender, who's trying to send a message X to Bob. However, the problem is that the channel is noisy. What do I mean by that? I mean that there's an adversary, Eve, who is allowed to corrupt some of the communication between Alice and Bob. Specifically, Alice is allowed to erase some of the bits, or Eve is allowed to erase some of the bits that Alice sends to Bob by replacing them with a blank symbol. So one of the common questions asked in information theory and coding theory is, can Bob still learn X if Eve is allowed to erase a constant fraction of the communicated bits? Obviously, if Alice just sends over the message X directly, then the answer would be no, because the adversary can simply delete one of the bits, and then Bob cannot uniquely determine what X originally was. However, using an error correcting code, Alice, instead of sending her message X directly, sends an error correcting code. Then Bob can decode X even if a small, say 0.1 fraction of the original message was erased. So I'm sure most of you have seen error correcting code so far, but let's go through the definition a little bit for our talk. So Alice's original message will be in 0, 1 to the K. The function ECC, error correcting code of it, maps 0, 1 to the K to a longer string, 0, 1 to the N. That Alice sends over to Bob instead. This message is considered to be alpha erasure resilient if for any alpha fraction of the bits that Eve erases, Bob will still be able to uniquely determine what the message X originally was. ECC has a relative distance alpha if for any two possible messages X and Y that Alice could have sent, the fraction of bits on which they differ is at least alpha. It's worth proving to yourself that these two parameters are actually the same. The relative distance is the same as the erasure resilience. So the first question that one might try to ask about error correcting codes is, what is the maximum value that this erasure resilience alpha can attain? And it turns out there's a clean answer to this question, that as K gets large, so as K goes to infinity, no error correcting code has relative distance greater than 1/2. Specifically, I write 1/2 plus little o of 1, where the little o of 1 goes to infinity as K goes to infinity. And if you want to think about how to achieve a distance of 1/2, it might be a useful heuristic. It's achieved by a random code. What I mean by this is for every possible message Alice could have sent in 0, 1 to the K, she chooses a random message in 0, 1 to the N, where N is much larger than K, that her message encodes to, and for N much larger than K, the closest pair of messages will be distance 1/2 apart. So of course, I only told you about this clean lower bound in order to ask the following question. Can we achieve upper bound? Can we achieve a higher erasure resilience than 1/2 under relaxed assumptions? Specifically, can we achieve a higher erasure resilience if we allow interaction? So before we actually think about whether we can achieve this erasure resilience, we need to precisely define what it means to have an interactive ECC, or as we'll call throughout this talk, an IECC. So like in the previous setting, Alice has a message X that she wants to send to Bob, but there's no reason that it needs to be the case that Alice is the one sending all of the bits. All of the bits are from Alice to Bob. Instead, Bob could be sending some of the bits as, quote, feedback. So the precise model is that Alice and Bob agree on a protocol length and an order of speaking. Then they, based on their private input and everything they've heard so far, they send bits in each round that they are supposed to speak in. The adversary Eve is allowed to corrupt, i.e. erase, messages from either party, and the protocol is said to be alpha erasure resilient if Bob will always output X correctly, so long as less than alpha fraction of the total bits are communicated. Specifically, this means that Eve is allowed to corrupt as much of is allowed to corrupt as much as she wants of either party, as long as it's less than alpha of the total communicated bits. She could purely corrupt Bob or purely corrupt Alice if she so chooses. In this way, we're allowing her the least possible freedom. Nevertheless, this model is strictly more general than a regular error correcting code, because an error correcting code is just an IECC where Alice must send, where they pre-agree that Alice sends all of the bits. So now the question becomes, what is the maximum fraction alpha of adversarial erasures that the IECC can be resilient to? Specifically, can we do better than a standard error correcting code, which, as we showed earlier, achieves an error resilience of about half? So let me try to convince you that the answer to this question is no. So what have we given Alice and Bob when we allow an interactive protocol rather than just a singular long message from Alice to Bob? We basically said that we are replacing Alice's messages with Bob as follows. So if Eve's corruption budget is fixed at some value alpha, then we've just replaced these messages where Alice, who actually knows what the input is with some messages from Bob, who doesn't actually have any information about what the input is. So a priori, Bob's messages are much less useful, which makes us believe that maybe this is impossible. I mean, maybe the feedback could be useful, but like the problem here is that like this feedback can actually be corrupted as well. So Alice can't necessarily rely on it too much. And if she doesn't rely on it, then Eve can use the budget from Bob speaking to corrupt more than 1/2 fraction of Alice's messages. So, I mean, this is obviously not really a proof, but that's some intuition as to why Bob's feedback messages are not actually that helpful. They like eat into time where Alice could be talking and still allow for Eve to corrupt. However, the main theorem of our paper is that there actually does exist an IECC that is resilient to greater than 1/2, specifically 3/5 of adversarial erasures. So the main result of our paper is that protocol construction, an IECC that is resilient to 3/5 erasures. We do have a couple of other results that I will outline in the slide before we get on to the actual explanation of our protocol. We also show an impossibility result that no protocol can achieve greater than 2/3 error resilience, but note that there is a gap between 3/5 and 2/3, so it is an interesting open problem as to what the actual correct bound is over here. The other thing one could consider is the bit flip case. This is the case where instead of erasing messages, the adversary Eve is allowed to flip 0s to 1s and 1s to 0s. In this case, the non-interactive error correcting code would give Alice and Bob an error resilience of 1/4. Moreover, we are able to show an impossibility result that no protocol can do better than no even interactive protocol can do better than 2/7. So it is also an interesting open question as to whether one can beat the protocol construction of 1/4 using interaction. I'll also note that the protocol in our paper requires O of k squared communication complexity and O of k rounds. Two of the authors, Gupta and Zhang, later improved this to a protocol that still has greater than 1/2 erasure resilience, but requires O of k rounds, or O of k communication complexity and O of log k rounds. Today we're going to be talking about the O of k squared communication complexity problem for this paper, and also we're going to be talking about a slightly simplified version of the protocol, which achieves an error resilience of 6/11 rather than of 3/5. So let's begin the discussion of our protocol. So before we move on to the solution, I'm going to quickly restate the problem. So Alice and Bob are engaged in a fixed order fixed length protocol that is determined before Alice and Bob before Alice gets to see what X is, such that at the end of the protocol, Bob will output a value X that is Alice's input. What is the maximum fraction alpha of adversarial erasures that Alice and Bob can be resilient to? And then Bob is still guaranteed to be able to output X. All right, so let's just quickly dive into the general idea of the protocol. The protocol is essentially going to consist of 3 steps, and the first goal will be to make each of these individual 3 steps resilient to greater than 1/2 erasures. In the first step, Alice sends over ECC of X to Bob. Obviously, if Bob wanted to uniquely decode it, that would not be possible because the adversary could block that by erasing 1/2 of the messages, as indicated by the impossibility result on non-interactive communication. Instead, he's going to decode it to 2 possible consistent values, X0 and X1. Next, he's going to compute an index I such that his 2 possible values, X0 and X1, differ on the index I. Then he's going to somehow send this to index to Alice. We're not going to talk yet about how Bob does this in a way that's resilient to greater than 1/2 error, because that's a little bit more involved. But let's just assume that he can. Then finally, Alice is going to send over Xi. And because Bob knows that X is either X0 or X1, and both those values differ on the index I, Bob will be able to successfully decode Alice's message so long as he hears at least 1 bit of the message that Alice sent. Because if he hears a single 0, then he knows that the entire message was 0, and if he hears a single 1, he knows the entire message is 1. So in fact, the final step is resilient to fraction 1 of erasure. 1 minus epsilon to be precise. Let's talk a little bit more precisely about the first step as well. So if Bob only wants to list decode Alice's message to 2 options, it turns out that the step is resilient to 3/4 erasures. Specifically, what I mean by that is if Alice communicates it as smartly as possible, then any adversary trying to erase less than 3/4 of the messages will not succeed, and Bob will be able to decode 2 consistent values, X0 and X1. All right, so I guess there's 2 things that are remaining. 1, we don't know how to make step 2 resilient to greater than 1/2 error, and 2, even if we can make the individual parts resilient to 1/2 error, it's not totally clear how to design a protocol. Let's address the second problem first and design a protocol based on these 3 sections. So our protocol, so the non-obvious thing about the protocol is that if we just divide the protocol into 3 chunks like this, like 3 rounds, then the adversary could just corrupt the shortest round entirely, and then that round will just never happen. So we need to make the rounds variable. So what Alice is going to do is she's going to keep sending ECCX to Bob until he actually receives the message. By receives the message, I mean that he decodes only 2 consistent values, X0 and X1. If we imagine that, in other words, less than 3/4 is erased. If we imagine that Bob's messages are much shorter than Alice's, then let's say like 0.1, let's say like 0.1 of the length of Alice's messages, then if the adversary is only corrupting 6/11 of the messages, then eventually Eve will have to let through at least 1/4 of the message from Alice to Bob. Otherwise, she will be corrupting more than 6/11 of the messages if Alice is the one who's doing most of the speaking. So eventually we will get through this section of the protocol. Next, Bob is going to send over ECCI until Alice uniquely decodes I. This has a giant asterisk next to it. This procedure doesn't actually work because obviously if the adversary is just trying to, because obviously the adversary could just erase half of Bob's message, which is like basically no corruption, and Alice will not uniquely decode I. But we'll get to the fix for that section later. And then finally, once Alice knows what I is, she just sends over xi for the rest of the protocol. And by the same logic as step 1, Bob will eventually receive Alice's Bob will eventually receive a message of xi that is less than 3/4 erased. And in fact, from that, he will be able to tell what the message was uniquely, since there are only 2 possibilities, the all zeros and the all ones message. So basically the point is, if a section of the protocol is being corrupted a lot, it extends in length until it has been completed. So the question now becomes, how do we do this second step? So there's essentially the following attack that's occurring on the second step that we need to avoid. Alice is sending over ECCX in every message, and then at some point when Bob figures out what X0 and X1 are, then he sends over ECCI. The adversary still needs to be corrupting 1/2 of Alice's message in order to prevent Bob from uniquely decoding X, but he also can only corrupt 1/2 of Bob's message, and then Bob will continue to have 2 possible values for Alice's message, and Bob will continue to have Alice will continue to have 2 possible values for the index I. So this is a problem because it's only 1/2 of each party, and therefore 1/2 corruption overall. So the thing that we could try to wish, one thing we could try to wish for is to have Bob's messages be relative distance greater than 1/2. So the problem right now is Bob is trying to send one of many possible things, and therefore the closest 2 of the possibilities he could be sending are distance 1/2 apart by the non-interactive upper bound we had earlier. However, if Bob were only sending one of 4 possible messages in every step, namely zeros, which we'll call for the rest of the talk, 0 star, 1 star, 2 star, and 3 star, we could make these messages distance further apart. Remember that the 1/2 upper bound only applies when the number of possible messages that a party could be sending goes to infinite. So let's say that we were able to make Bob's possible messages distance 2/3 instead of distance 1/2. Then the attack of corrupting 1/2 Alice and 1/2 Bob no longer works. You would now have to corrupt 1/2 Alice and 2/3 Bob. So this is actually where the 6/11 comes from, because if you balance this with the other attack, which is just to corrupt 3/4 of Alice, so that Bob can never learn 2 possible values for Alice's input, then if you make the message ratios 8:3, you get that in order to execute either one of these attacks, the adversary would need to corrupt 6/11 of the messages of the bits in the protocol in total. So basically what we want to do now is we want to have Bob able to communicate the message I to Alice while only sending one of 4 possible messages instead of actually explicitly sending over ECC of I. So if you just wanted to have Bob communicate the message I to Alice in one message, then he obviously can't do this with 4 possible code words, because there are more than 4 possible values of I. However, he can use many messages to do this over the course of multiple messages. What's going to happen is Alice will keep track of the counter C that is initialized to 0, and Bob will use multiple messages to try to increment this counter to I. Basically, Alice sends over her counter C in every message, And then Bob will send over either 1 star or 0 star to tell her whether to increment the counter or not. We're not even going to use the extra 2 code words, 2 star and 3 star just yet. Those will be for later in the protocol. So it's written on the slide exactly what procedure Alice and Bob follow, but that's not super important. The point is, Alice will be receiving, or Bob will be receiving Alice's value of counter, and then he's going to tell her whether or not to increment until she actually reaches the correct value of counter, which is I, and then he's going to tell her to stop incrementing. And the 0 star or the 1 star will be the instruction of whether to increment or not, and the rules for that are highlighted on this slide. The ultimate point of this is that Alice and Bob will make progress towards their shared goal of Alice learning I if Bob is able to uniquely, if in a chunk, Bob is able to uniquely decode Alice's message, and then Alice is able to uniquely decode Bob's message. The second condition, Bob decoding Alice's message, requires less than 2/3 of Bob's message being corrupted, which is better than the original 1/2 that we had. However, it seems as though we're still chasing our tail, because we still have this problem that Bob needs to uniquely decode Alice's message, and Alice's message is still one of many possible things, because the counter could be one of a very large number of things. So there's only distance 1/2 if you just do what we're showing here and sending over an error correcting code of the counter. However, it turns out that we're actually done chasing our tail, and this procedure will actually be able to be used, even though Bob is going to have multiple possible values of Alice's input, x0 and x1. It turns out that we can actually pretend he only has one possible value of counter. So let's use this to construct the final protocol. And even though our procedure requires Bob, our implementation procedure will require Bob to uniquely decode Alice's value of counter, it'll suffice. So in the final protocol, Alice is going to send over ECC of x and her counter value c, which is initialized to 0. She keeps doing this until Bob receives a message that is less than 3/4 erased, and therefore finds 2 consistent values, x0, c0, and x1, c1. And then we perform the incrementation procedure, assuming that c0 and c1 are always equal in every message that Bob receives that is less than 3/4 erased. Then eventually Alice is going to send over ECC of x, I, and Bob will receive this because her value has reached I. Then Bob sends over his third code word, 2 star, to indicate to Alice that she has successfully sent over the message, that she has successfully reached the counter value of I. Then Alice sends over xi for the rest of the protocol. And as we said earlier, Bob will eventually receive a single bit of this message at least, and therefore will learn which of x0 and x1 was real. So now we need to look at the case where at some point c0 is not equal to c1. Note that every time Alice is incrementing her counter, so the first time that c0 and c1 differ, they differ by exactly 1. If this ever happens, then Bob sends over his fourth and final code word, 3 star, to tell Alice that all he cares about now is learning what the parity of her counter is. Because if he can figure out the parity of her counter, then he can figure out which of c0 and c1 was real, which in turn tells him which of x0 and x1 was Alice's true value. And then so instead of sending xi for the remainder of the protocol at that point, Alice will just send c mod 2, and by the exact same logic, Bob will eventually receive this bit and know which of Alice's what Alice's value of c mod 2 is. So in conclusion, I've told you about a protocol that achieves greater than 1/2 erasure resilience for Alice to send over a message x to Bob by exploiting interaction. There are a few open problems still in this field, namely, what is the best possible erasure resilience achievable by an interactive protocol, and what one can do in a bit flip setting rather than the erasure setting. I hope you've learned something, and I hope people are inspired to work on this problem in the future. Thank you.